Lesson 4-3.
Triangle congruence by ASA and AAS.
Now we're going to start with postulate 4-3, which is ASA. That stands for angle side angle postulate. The postulate states if two angles in the included side of one triangle are congruent to two angles in the included side of another triangle, then the two triangles are congruent. As you can see, we have angle H congruent to angle K, and angle J congruent to angle N. So, therefore, line segment HJ is congruent to line segment KN. In conclusion, triangle HIJ is congruent to triangle KLM by ASA. That's it. Now name two triangles congruent by ASA. We have triangle PRW, triangle ACY, and triangle MVB. What triangles are congruent by ASA? A is an angle, so we have all our angles congruent. Side, which is the included side, so this has an included side. This side isn't included, but this side is. So automatically we know that these two triangles, which are triangles P, R, W, is congruent to the triangle A, C, Y by ASA.
We are going to prove the angle side angle postulate.
Now we're going to learn how to prove ASA. We are given that line segment PQ is parallel to line segment RS. We are also given that angle PRQ is congruent to angle SQR. Now we are supposed to prove that triangle PQR is congruent to triangle SRQ. And here's our diagram. The first thing we're going to do is we're going to separate the triangles. Continuing with our proof. So I separated the triangles into two, so it would be easier to tell the sides congruent and the angles congruent. So we have line segment QP, and that is congruent to line segment RS. So let's put that in our statements. And the reason is because it's given. Another given statement that we can say is angle PRQ is congruent to angle SQR. And we already put that in our diagrams. Next, let's look for another angle. This angle is most definitely congruent to this angle, and that's because in this diagram you can tell because they are alternate interior angles. So, angle PQR is congruent to angle SRQ by alternate interior angles theorem. So, we have two angles and we have one side, but it's not included. So what do we need? We need another side. Let's pick side line segment. Let's pick line segment QR and line segment QR. They're congruent to each other by the reflexive property of congruence. So again, let's put this in our statements. And the reason, as I just said, is the reflexive property of congruence. And that sign shows congruence. So we have our angle, side, angle, and our angle, side, angle. Therefore, triangle PQR is congruent to triangle SRQ by ASA. And that is how you show that triangles are congruent by ASA.
Theorem 4.2, angle, side theorem, which states if two angles and a non-included side of one triangle are congruent in two angles and the corresponding non-included side of another triangle, then the triangles are congruent. Angle Q is congruent to angle T. Angle R is congruent to angle V. And line segment QS is congruent to line segment TU. So that means that triangle QRS is congruent to triangle TVU. By the theorem 4.2, angle, side theorem.
Which triangles are congruent by AAS? In AAS, we have to have a congruent angle, another congruent angle that's also included, and a congruent side. So we have triangle 1, 2, 3, triangle 4, 5, 6, 7, 8, 9, and 10, 11, 12. Triangle 1, 2, 3, we have two angles and a side, and that one angle is also included. So this one works. In this one, we only have one angle and one side, so that couldn't work with any theorem or postulate. In this one, we have two angles, which are good, and a side. One angle is included, so it works. In this one, we have another angle and another side, both in different places, but there's only two. Therefore, that means triangle 1, 2, 3 is congruent to triangle 8, 9, 7 by AAS.
Now we're going to prove the angle, side theorem. Proving ASA, given angle NER is congruent to angle NVR, and RN bisects triangle ERV. And we must prove that triangle ENR is congruent to triangle VNR. Angle ERN is congruent to angle VRN by the definition of angle bisector. We're going to mark our diagrams. Step 4. Triangle ENR is congruent to triangle VNR by angle, side.
Lesson check.
Lesson check. Number 1. What is the definition and how do you prove the ASA postulate?
Here, problem 1 is the definition of ASA, and that is that triangles must have two congruent angles and one included and congruent side in both triangles. And the definition, or what it stands for, is angle, side, angle. The answer to problem 2 is the definition of AAS, and that stands for angle, angle, side. The definition is that triangles must have two congruent angles, one of them being included, so right here and right here, and a congruent sides. Congruent, name the angles and or sides, and if the triangles are congruent, how? The answer of this equation, it's best to separate the triangles. So, we have triangle T, W, Z, and triangle A, W, Y. Line segment TW is congruent to line segment AW. So that'll be our first side. TW is congruent to AW. Next, we have our angles. As we already know, angle T is congruent to angle A. But now, what else is congruent? There's two W's on the top of each triangle, signifying they're congruent. They are also vertical angles in our first diagram. So, triangle TWZ is congruent to triangle AWY by angle, side, angle, that's ASA. And that's our answer. Continuing on with our lesson check. For problems 4 and 5, it asks, for proving the triangles congruent, would you use ASA or AAS? Problem 4. We have two angles and a side, and another two angles and a side. For these triangles, the included angle is right here, making it A. We start off with A as an angle as well, and we end with a side, making the triangles congruent by AAS. Next, for problem number 5, we have an angle, a side, and an angle. Another angle, a side, and an angle. The included side is in between the two angles, making it S, starting with an A and ending with an A, because the angles are also congruent. This makes these two triangles congruent by ASA. Thanks so much for watching, and I hope lesson 4.3 is very clear to you, and I'm glad we completed it. See ya!